about graphical analysis. And we're going to really review the graph shapes we've been using and add a couple new graph shapes, because as we move through this year, we're going to investigate other types of relationships. So that's where we're headed. Just recall that the whole purpose of making a graph is to show a relationship between two variables, if one exists at all. We're looking for trends, which is a general direction in which something is developing or changing. And I want you to start using a new level of sophistication. I've been talking about this all year, right? When you say, when distance increases, magnetic field increases, and you say that that means direct, that is oversimplifying the case. It's not that that's untrue. It just doesn't catch all the nuance that you really can discuss when we're talking about trends. So I'm going to ask you to be much more specific and talk about what type of direct relationship. How does X increase when Y increases? Is it doing that quickly, or is it doing it slowly? How slowly? How quickly? So we'll be able to kind of get a little bit more detail as we move forward. You know you're going to put a trend line on any graphs that you create. That is your best fit line. So a linear relationship we've been using all year. We're looking for a constant, which we call the slope, that makes those two values equal. The power on the x is 1. And when there's a power on something that's equal to 1, it's invisible, right? We don't write it. So y equals mx. When the y-intercept is equal to 0, then we can just leave it in that form. Inverse relationships we've been talking about also. So we have this coefficient, which I just use the coefficient a, it can be any number, and the exponent on the x is to the -1. Another way to write that, as we've been discussing, y equals a times 1 over x. So when you have a negative exponent, you're going to be expressing that in the denominator. So that's what a negative exponent means. So a new relationship we're going to be using is what we call a direct square relationship. It looks very similar to the previous one, except instead of having -1 as the power on x, it's a +2. This is a direct relationship, but we're increasing much more rapidly. An inverse square relationship looks also very much like the previous two, where you have an exponent on the x, but because it's to the -2 power, it means it's an inverse relationship. It means it's over x. So I could rewrite this. I'll do the same as I did in the previous one. Sorry, this is so childish, this writing. But so that's what the equation looks like. Instead of writing to the -2 power, you could put 1 over x squared, if that makes you more comfortable. Notice that the shape of this graph looks like the regular inverse graph, except it's a little more steep. You can't tell if it's inverse or inverse square without checking on Excel and checking the power fit trendline equation. There's no way to know from looking. This is also a new relationship that we'll start to explore a little bit. This is a square root relationship. The square root has a power to the 0.5 power. So we're increasing, right? It's a direct relationship, but you're increasing more slowly. So instead of curving up where you're increasing really quickly, or going straight where when one goes, the other goes the same amount, we're increasing much more slowly. No relationship we've been exploring. We mostly have this here where we end up with kind of a straight line, because as we change x, y doesn't change. We don't usually get these other ones very often. So how do you evaluate the best fit trend line? First of all, you want to look at the theoretical relationship. So look at your equation sheet. Find an equation that has both the variables that are on the x and y axis in the equation and see what is the theoretical relationship between them. The other way that you can evaluate them is by using the r² value, that correlation coefficient. The correlation coefficient tells you how closely the data that you collected fits the trend line that you chose. Occasionally, you're going to see an RMSE value on capstone. An RMSE value is actually the inverse of a correlation coefficient. It stands for root mean square. So a root mean square is just saying how far your points are from the trend line. You have 0 points far from the trend line, which is the same as a correlation coefficient of 1. So they're opposites. So some common student errors regarding graphing. I bring these up to highlight things that you may do wrong so you can be proactive and avoid these. So when I give you a statement and it says this is a graph of A versus B, that's telling you that A goes on the y-axis and B goes on the x. It's always stated y versus x. When you calculate slope, if you have to do so, you must use 2 points. You may not find slope by y over x. It's delta y over delta x. It's the change in the y coordinate over the change in the x coordinate. And on the same note, the slope has units. If it's change in y over change in x, then it's your y units divided by your x units. So that's an easy way to see what's the meaning of the slope of that line. We haven't yet talked about area under a curve, but we will be doing so. So an area is like base times height is the most simple way to find area of a rectangle or a square. So you're taking the base, which is your x units, and you're multiplying it by your height, which is your y units. So if you need to find the units of an area, just do x units times y units, and you can figure that out, simplify if necessary. Here's the next requirements. If you're ready to move on to proficient, because you've already achieved developing, you can start moving yourself and doing some of these things. You can see the biggest difference between developing and proficient is you're using the correct feature and you're overtly stating its significance. Like you're writing out, why are you using the slope? Why are you using coordinate points? Why are you using the area? Whatever it is, you have to say why you think it's useful. And you would present the relevant physics relationship. So maybe you would pull it off your equation sheet and just write down what relationship you're using. This is a step-by-step guide to proficiency in graph interpretation. You may want to screenshot this and keep it somewhere handy in your physics folder and open this up when you're doing the next set of practice. I'm not going to read through all these. I kind of just verbalized the items that you need to do. And of course, I'm going to reinforce this on the guided practices that we do. When you're doing graph creation, we've been working on developing, and most of you did a great job with this. So you have to put the relevant independent and dependent variables on the axes. You label those axes with units and the variable, and you include a trend line. So to get proficient, the axes have to be labeled correctly. So you can't have them flipped. You can't have the wrong stuff on them. You're going to add reference values. Even if you don't have numbers, you're going to put like D1, D2, T1, T2, like just to give a couple coordinate points. And you're going to select your trend line by an overtly stated relationship. So again, you're going to take out your equation sheet. You're going to pull an equation that makes sense, that seems to be relevant based on the story that you were given and what you're graphing. And again, here is the step-by-step guide to proficiency in graph creation. So if you'd like to screenshot this, you might find it useful to kind of go step by step and do this thoroughly when you're practicing. The physics classroom has this great practice. I hope you'll go to this site and you'll use this concept builder, because some of you could really use some review in calculating slope and identifying words that describe the relationship and predict unknown quantities. So it's a really good practice and it's set up like a game. Okay, one note on selecting trend lines, specifically on Excel. Excel is going to allow you to choose the fit for the trend line. We've been doing this for months already. But here's the thing, they give you 6 choices. We only ever use 2. We use either linear for a linear equation, for direct, and power fits for any of the other ones we've talked about today, whether it's a direct square, a direct square root, an inverse square, or an inverse relationship. You need a power fit for that. You can use linear for no relationship also, but that's it. Please do not use any of these other ones. We will never really need this or this or this. We will talk about that there might be an argument for using polynomial. We'll talk about that a different time. So just to review the exponent on a power fit equation, what it's going to tell you. And we reviewed this when we were a little earlier, but again, you may find this very useful to screenshot. When you have a positive 1 power, it's linear. If it's negative 1, it's inverse. If it's positive 2, it's a direct square. If it's negative 2, it's an inverse square. If it's 0.5, it's a direct square root. If it's a negative 0.5, it means inverse square root. Now, when you do Excel, it's never going to come out to be exactly 2 or exactly 0.5. So you're going to need to look and probably round, because you might get like 0.629, and you know that you're going to have to round that to 0.5, or maybe it'll be 0.987, and it rounds to 1. So you have to use a combination of the theoretical equation to help you figure that out, plus what Excel tells you the exponent is. These are some great resources. If you'd like to know more about these and do some more practice, please take a look at these websites.